Hi, I'm Zor. Welcome to Unizor education. We gradually approach the matrix multiplication definition. Gradually, because I would like to define it in some special cases. Like in this particular case today, I will talk about square 2x2 matrices. You see, matrix multiplication is extremely important operation, I told you many times, because it's related to transformation, and it's a combination of consecutive applications of different transformations. So if you are applying one transformation and then another, basically it's an equivalent to multiplication of the matrices which reflect these transformations. So, what we would like to define right now is an operation of multiplication which satisfies this very simple rule. If you take the vector u and apply certain transformation, linear transformation, which is reflected in some matrix A, into vector v, then you can say that v is equal to u multiplied by a, or a multiplied by u. It depends on whether it's a row vector or column vector, whatever. But then if you have a next transformation into vector w, then you can say that w is equal to v times b, or a times u, or b times b, depending on. Now, what is really important is that the w vector is the combination of vector u and matrix A, and then the result is multiplied by matrix B. Or, from the other perspective, it's B times A times u. So, our purpose is to define matrix multiplication AB or BA in these cases such that W is equal to U, and then you apply the product of two matrices, or in this case you apply the product of two matrices in this way. These must be equivalent. So consecutive application of A and then B should be equivalent to single application of a product of matrices A and B. So that's what I would like to that's how I would like to define the operation of multiplication. I mean, that's the root of it. That's the understanding what's behind the definition. Because it's very easy to define an operation saying, okay, you do this, this, and this is called the product of two matrices. Why? Well, this is why. We have to satisfy this particular condition, so the operation of multiplication is, well, nice, if you wish. It's convenient to work with, and it's really reflecting certain material substance behind this matrix application. The substance being a linear transformation. Alright, so keep it in mind, and that's what I'm going to do with two-dimensional vectors and two-dimensional matrices, 2x2. So we would like to define a 2x2 matrices product in such a way that these conditions are satisfied. Alright, so what we do is we start with a vector u, u1, u2, and matrix first A, which has I, A, J coordinates, and I and J belongs to the interval 1, 2. So it's 2x2 matrix. A11, A12, A21, A22. That's how these elements of the matrix A are located. Now, then we apply matrix A to the vector u, and I will multiply it on the left. It's more convenient for me. And I will get the vector v. Now, how vector v is, how coordinates of the vector v are expressed in terms of u and matrix A? Well, this is something which we have already done many times. That's how coordinates of the vector u are related to coordinates of the vector v using the linear transformation described by the matrix A. So this is given to us. All right. Next, what's given is we have the B matrix, and the B matrix will be also expressed as Bij, and it's also 2 by 2 matrix. And I apply this matrix to vector v to get vector w. Which is related similarly to the v. So w1 is equal to b11 v1 plus b12 v2, and w2 is b21 v1 plus b22 v2. Now, what I was talking about before is a relationship between w and u. Can I get in one linear transformation from u to w? If I can, that would be some kind of a matrix C in such a way that C applied to u would give me w. That's what I would like to get. Now, if I will find this particular matrix of linear transformation which will convert u into w, then this matrix must actually be called a product of A and B, or B and A, depending on. All right? Okay, fine. Easy. Let's do it this way. Instead of V, we'll substitute this. Instead of V1, instead of V2, we'll substitute this. And let's see what happens. So it's B11 times A11 U1 plus A12 U2 plus B12 V2. V2 is this. A21 U1 plus A22 U2. Now, W2 is equal to B21, the same thing here, plus B22, A21 U1 plus A22 U2. Okay. Now we just have to combine U1 and U2 to get something reasonable, right? So let me just wipe out this thing. So what I will get is W1 is equal to something multiplied by U1. Now, what is multiplied by U1? B11 A11, B11 A11, B12 A21. U1, and U2 would be B11 A12 plus B12 A222. Okay. W2 equals to similarly, B21A11 plus B22A21. U1 plus, now with U2 I have B12A12, B21A12, B21A12, and B22A22. Okay, that's all I need right now. So if I'm looking for a transformation from vector U to vector W with some matrix C, then these are my coefficients, right? I already expressed it this way. So C11 is this, C12 is this, C221 is this, and C22 is this. So this is basically a definition of my multiplication, because since W is equal to B times V, B is matrix, V is vector, V in turn is equal to A times U, A is matrix, U is vector. On another hand, I have that W is equal to CU. So it's very natural where C is expressed in these ways. So it's very natural to say that C is equal to B times A, because that would actually give me exactly what I want, meaning that the product of two matrices is a one single transformation which combines in itself two transformations consecutively applied. First A and then B. Okay? And this is a definition of this multiplication. So how can I find out what is in a 2 by 2 case? By the way, we are all 2 by 2 cases. A, B, and C are all matrices with 2 rows, 2 columns. How to find the coefficient C11? This how. So that's how the matrix B is multiplied by matrix A. Each particular element of the matrix C, which is the product, is defined by using these definitions. But let's take a little closer look at these definitions. Look at this. C11 equals to B11 A11 plus B12 A21. Okay, let's think about how it looks. We don't need any more of this. All we need is this definition. Let me write it down. B11, B12, B21, B22. This is my matrix B, and I'm multiplying it by matrix A. And I'm getting C11, C12, C21, C22. Right? So C11 is equal to B11 times A11 plus B12 times A21. So I'm taking the first row and the first column. And notice this, element index is 1, 1. Now, I will use the following notation for the row vector, let's say the first row vector b, I will use b1 and then I'll put an asterisk, and this is a vector, which means b11, b12. And the column vectors, where the second index, actually the column index is the same but the first one is changing, I will use this notation, star 1 in this case. So what I can say is the following: this is equal to b1 asterisk, which is the first row vector, scalar product, because this is looking actually like a scalar product of two vectors, right? b11 and b21 are components of one vector, and a11 and a21 are components of another vector. Which one? This vector. So I'm taking the first row multiplied by first column vector. So again, the C11 equals to scalar product of the combination of scalar product of first row vector and first column vector. Similarly, C12 is equal to C12. It's equal to B12 A 12. Stop. No. C12 is equal to B11 A21 plus B12 A2 the first column 2, right, which is equal to, this is the formula, one of those which I have wiped out. I shouldn't really, but that's what it is, which is b1 asterisk row, the first row vector, and the second column of the A matrix. So again, you see, these 1 1 and this is 1 1. This is 1 2. This is 1 2. And same thing will be for 2 1, which is the second row B21 and the first column A1 plus B22 A 2 1 equals to B2 asterisk times A asterisk 1. Again, indices of the product element here correspond to row vector and column vector of the components. And finally, the third one is, the fourth one is, it would be second row from the B and second column from the A, which is B21 second row and second A12 plus B22 A22, which is B times A second row vector and second column vector. So that's the rule which I actually would like you to notice, that whenever we are multiplying 2 by 2 matrix by 2 by 2 matrix, we get 2 by 2 matrix, and each component of this 2 by 2 matrix, which is the product with indices ij, where both I and j can be either 1 or 2, is equal to i's row of the B matrix row vector scalarly multiplied by j's column vector from the matrix A. and this represents multiplication of two matrices. So that's my final result for today, which I would like actually you to remember, because this would be applicable to anything else. So if you would like to have an element ij of the product of two matrices, then you have to take the i's row vector of the first matrix and multiply it as a scalar product to j's vector, a column vector of the second component of the product. So what I'm going to do, my plan is to show that this rule is exactly the same for 3 by 3 matrix. That would be next lecture. And then based on this I will define, basically I will do exactly what many teachers do from the very beginning. They're saying, okay, this is a definition. These formulas are the definition of the multiplication, and they don't explain why. But why is very important. Why is, the reason behind this is that the multiplication of b times a should really produce exactly the same transformation as consecutive application of a and then b to the vector. Whatever the vector is, doesn't really matter, doesn't depend on the vector. So that's basically the result of this lecture, which I would like to extend in the next lectures into a full definition of the product of any two matrices, not necessarily square and not necessarily 2 by 2 or 3 by 3, etc. Okay. Don't forget that Unizor.com has not only this lecture but also notes for this lecture. And for those students who register, obviously you can have exams taken, and you can have your supervisor registered as your supervisor to basically enroll you or make some into some courses, or mark certain courses as completed if he or she is satisfied with your exams. So basically it's like an educational process which you can get engaged with the help of your supervisors, teachers maybe, or parents. So that's it for today. I do recommend you to read the notes again, because they are in relatively better order than I put it on the board. And then attend my next lectures, which are related to other aspects of matrix multiplication. It's very, very important operation, the most important operation on matrices. That's it for today. Thank you very much, and good luck.